So let's look at one last example of using this technique we're talking about to evaluate the integral of a rational function. So, if we look at the example we have here on the board. It's 2x to the fourth plus x cubed plus 12x squared plus 2x plus 15 divided by x minus 1 times x squared plus 3 all squared. Right, so you see the difference between this example and the previous one is that here we have a repeating quadratic. Right. So in principle it doesn't make things much worse, except that, well, we have now more unknowns. Now in this case we have 5 constants, a, b, c, d, e in our expansion. Right, so remember, right, we write down our expansion and we look at the factors of the divisor of q. Right, so we can write p over q, right, and we have this linear factor, x minus 1, so that's a over x minus 1. Right, and then this quadratic term repeats. So we have bx plus c over x squared plus 3, right, and we have dx plus e over x squared plus 3 all squared. Right, so if we had, say, x squared plus 3 cubed, we would have another term here, say, fx plus g over x plus 3 all cubed. Right, so luckily we don't. It gets quite complicated computationally. Right, so I've gone ahead and written down the expansion. And remember, then we add this fraction back together, putting it over the common divisor q. Right, we multiply out, we group like terms together. Right, so that's what I've done here beforehand. Right, so we get an a plus b x to the fourth. Right, we get a c minus b x cubed. And we get a 6a plus 3b minus c plus d x squared. Right, we get a 3c minus 3b plus e minus dx. And a 9a minus 3c minus e, all the constants. Right. Now remember, so we have p over q equals this whole mess over q, and so p must be the numerator here. Right, so the like terms here should have the same coefficients as there. So here we have a plus bx to the fourth, here we have 2x to the fourth. So a plus b equals 2. And similarly for the other terms. Right, so let's write down the equations. Right, we have a plus b equals 2. We have c minus b equals 1. Right. Then we have 6a plus 3b minus c. C plus d. That has to equal, right? So we have 12. Right, and then we have, for the x's, 3c minus 3b plus e minus d, and that equals, for the x's equals 2, and the constants, 9a minus 3c minus e, right, and that has to be 15. Right, so 1, 2, 3, 4, 5 equations in 5 unknowns. Right, and that can get quite computationally tricky to solve. Right, so let's see when we do that. Oh goodness me. Right. Well, let's see. Well, I've actually gone ahead and written down what we should have here. But if you solve these, we get a equals to 2. Right. We get d equals to 1, e equal to 0, and lastly we get b equals to 1, c is also 0. Right. So in principle this is easy to solve. Right. We do it just like we did in the previous two examples. The only difficulty is that we have 5 equations and 5 unknowns. Right. So it's not difficult, but it's tedious, and I need a lot more blackboard space than I have available here to do that. Right. So in principle we can easily find these constants. Right. So let's now see if you write down the integral. Right, this integral becomes the integral of. Right, so we have a equals 1, a equals 2, so that's 2 over x minus 1. Right, and then we have e and c equals 0, d and b both equal 1. So we have 1 over x squared plus 3 and 1 over x squared plus 3 all squared dx. Oh, sorry. That's x. That's an x as well. So integrating this, first expression gives ln, or 2 ln, x minus 1. And second one gives 1/2 ln x squared plus 3. The last one gives 1/2 minus 1/2 over x squared plus 3 plus c. Right. So the only difficulty here is in solving these equations. Right. And again, in principle that's easy, right? But in practice, right, it's computationally a little challenging because you have so many variables and so many unknowns. Right.